Alright, hello, welcome to another video for this chemistry course. And we have spent a lot of time talking about electron configurations recently. We've been focusing on the electron and the importance of it, especially the valence electrons, as those are the electrons that are involved in reactions in forming compounds and forming the bonds that keep those compounds stable. So we are going to continue to talk a little bit about electron configurations, but we're going to tie it into a previous discussion about the periodic table. I think we've mentioned a little bit about the periodic table already and some of its trends. And now we're going to look at what is the connection between electron configurations and the arrangement of the periodic table. The periodic table is such a powerful, powerful tool for scientists, and it is arranged in a kind of a peculiar manner. We're going to investigate why that is and how it is connected to the electron configurations. All right. So if you notice right here, if you've read this already, it says the periodic table is a bit odd, which is true. It's not square, it's kind of a unique shape. Large portions of the table appear to be missing at the top. It's not organized in what would appear to be a reasonable or logical fashion. It's not alphabetical, but there is a reason behind all of the establishment of the periodic table, the direction of the periodic table, the arrangement of the periodic table. So it is organized by properties, meaning that chemical and physical properties are similar for all of the elements in a particular group. But we're going to also dive in and we're going to figure out why that is. We're going to look at the atomic structure, specifically the electron configuration. What makes all of those elements in a particular group have similar chemical and physical properties? Okay, so the properties, these properties are tied into, are connected to the electric structure, the electronic structure of the atom. Okay. In Model 1 we have a blank periodic table, and there is some information that is given about different sections or areas of that periodic table. We'll talk about that in a little bit. If you did this already, you would have found in this assignment, in this particular unit, there would have been some documents that kind of assigned a group, a particular, like a student group, meaning a particular group on the periodic table, and then gave you some information. So those documents are available to you in the course, and hopefully you use those. If you didn't, that's okay. We can do this together. We'll walk through it together and use those different groups to kind of help us understand the connection between the electron configuration and the periodic table. So it says right here, obtain a card with electron configurations for your group as assigned by your teacher. Again, as mentioned, if you saw that card in the course, it would have been something like this. And each team, if you're working at a school or you're working at home, you can assign different people in your group a particular group number on the periodic table. So you could assign them different group numbers here, or team numbers, and then they would be assigned a particular group on the periodic table. Okay? So you have 1A, you've got 8B, the F block sample, here you've got 7A, 2A, 5A, etc., etc. Okay? And it kind of gives you a sample of the elements that would be in that particular group. So if you've been assigned that, you would just hear it says record your team number. So okay, we got team number 2, and if I look back at this card, team number 2 is the group 8B, which is iron and cobalt, nickel, etc. here. So I've got the, what was it? 8B, okay? But you can do whatever you want to with that card, and but they are assigned for a particular reason, because we want to look at how there is similarity in all the elements in a particular group. For each element on your card, write the last orbital notation appearing at the end of the configuration. What that means is we're going to look at the electron configuration for everything in that particular group. So let's take one that's really simple. Let's take this first group right here. This is group 1, number 1 here. And if you remember, in the box for that particular element, I'm just going to write the last part of the electron configuration for that element. So this would be hydrogen right here. Well, the electron configuration for hydrogen is 1s1. It has one electron. That one electron is in the first energy level in the s orbital. This next element here, it would have filled the 1s orbital, because you'd have 1s1, then 1s2 over here, and now we're on the second energy level. We're starting to fill the s orbital. You'd have one electron in that 2s orbital. I'm not looking at the other part of that electron configuration. I'm just looking at the last section, the last part of that electron configuration. I know it's got 1s2, but it ends in 2s1. This one down here, we're in the third energy level, and I would have filled the 1s2, the 2s2, the 2p6, and now I'm at 3s, and I'm starting to fill 3s, so I have 1 in there, 3s1. And you can kind of see the pattern that's happening here. This element here, it would end, its electron configuration would end in 4s1, 5s1, 6s1, and 7s1. Okay? So I just did it for group 1. What it says here is write the last orbital notation appearing at the end of the configuration, the underlined portion. Again, in the assignment there is a document that shows, so for example, if I did team 1, the alkali metals here, I would see the underlined portion here is what I'm focusing on. Okay, so that's all in the course for you to look at. So we actually did with team number 1, and we actually did the alkali metals or group 1 on the periodic table. Okay, and these all are going to end in like 1s1, 2s1, etc. What is similar about the last orbital notation appearing at the end of the configuration for each element in your set? So basically what's similar is we are filling a very similar orbital, it's just that it is at the next energy level. So they have a very familiar and similar ending, and remember those electrons that are at the end, those are kind of serving as the valence electrons. Those are involved in reactions. So it makes sense that those elements are going to have similar chemical properties. So these are all ending in S1, something S1. And this number right here would be the energy level. I'm sorry, energy level. So it's going to be that particular energy level and then S1, something S1. All right? Locate where your set of elements would be in model 1, and we did that already. Write the last orbital notation in the electron configuration for each element in your set as in its respective box. So we did that already as well. We did 1s1, 2s1, etc. What is the relationship between your answer in question 2 and the block of the table where your set of elements is located? Well, they have told us that this is called the S block, meaning, if you see it's in bold outline here, this is the S block. Well, why would this be called the S block? Let's go on to the second group here. Let's imagine that you were assigned this second group here. Your team is assigned this. All of the endings for this, and we'll refer to the document in the course as well. If you were given team, actually I think it would be here. Team 5 is given the alkali earth metals. That's group 2 on the periodic table. Look at how they end. 2s2, 3s2, 4s2, 5s2, 6s2. All of them are ending in an energy level number and then s2. So this is 2s2, 3s2, 4s2, 5s2, etc. So you can see that in this group here, they all have a similar ending in that the s orbital is completely full, has 2 electrons in it. Remember, there's a maximum of 2 electrons per orbital. So if we go now and we look at the block, then is telling us, the block tells us the ending of the configuration. Okay, it tells us where the valence electrons are, where those valence electrons are located. It kind of tells us what orbitals have just been filled, or what's the last orbitals to be filled in the arrangement of that particular atom, in the electronic arrangement, the electronic configuration. Okay, so the block here is kind of an indication of what is being filled. Where are the electrons most recently placed in those particular atoms? What is the relationship between the last orbital notation in your set of ground state electron configurations and the row number on the left-hand side of the periodic table? So if we look here, the row number, this is your row number, 1, 2, 3, 4. Well, this large number, that coefficient there, that large number is telling us the energy level. So the row number and the energy level is telling us, it's giving us the same number, at least for the S block. Okay, for the S block, that is very true. So for the S block, this large number is always going to be the same as the row number. Okay, and everything in group 1 is going to end in energy level S1. Everything in group 2 is going to end in energy level S2. Actually, row number also, row number S2, row number S1. Let's go over here to the P block, and let's do some of these over here. Okay, here we have the group that involves nitrogen, and this one here, you'll notice that it's ending in 2p3. So let's find out where nitrogen, the nitrogen group, would be on the periodic table. Well, nitrogen would actually be right here. This is your nitrogen group. Okay. That nitrogen group, they're all ending in something P3. So for example, in the second row, this would end in 2p3, 3p3, 4p3. Let me go back to that card there. Look at all of these here. Nitrogen ends in 2p3, phosphorus 3p3, 4p3, 5p3, 6p3. So they are all ending in the row number, which remember is the energy level, and then P3. Okay? Let's find another one that ends in P here. Here we have the noble gases, and that is the last group, the last column on the periodic table, and they're all ending in P6. P6, 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 2, 3, 4, 5, and 6 P6. So if we were to fill those in, this is 2 P6, 3 P6, 4 P6, 5 P6, 6 P6, and this would be 7 P6 if there was one, if there was an element there. By the way, helium here just ends in S2. It is actually 1s2. So actually, to put it in the correct group for matching its electron configuration, this would be placed over here in that location. But the reason why it is in the last group is because it behaves like the other noble gases, because its outer energy level is full. The s orbital, 1s orbital, is full with just 2 electrons. So it behaves like the other noble gases whose outer energy level is all full. So the p orbitals are full once you have 6 in there. There are 3 p orbitals, each having 2 electrons, so it's full when you have 6. So that's why the helium behaves like it, because its 1s orbital is all full with just 2. That's all it needs. So it behaves like these other noble gases. That's why it's in that group. So if I was to guess, without even looking at the cards, I would guess that this group right here all ends in P1. And this one would end in P2. We got P3. This would end in P4. And this would end in P5. And I could just fill all these in. 3P1, 3P2, 3P4, 3P5, and you get the idea as you just fill those down as you go. So this is your P block right here. This is the P block. Why? Because in that block of elements on the periodic table, you are starting to fill and will eventually fill the p orbitals in the different energy levels. Okay, so the outermost electrons are in the p orbitals in those electrons, that particular block on the periodic table. Now you can guess what's going to happen here. In the transition elements here, it's called the D block. Why? Because the D orbitals are being filled. And down here you've got the F block. Why? Because that's where the F block, the F orbitals are being filled. And we can see that when we look at our different groups here. So here is, for example, the if you were teammate, you got the rare earth elements. Okay, you can see we're filling the F orbitals here with these elements. So if we were to go back to the periodic table, elements in this block down here, these are called, by the way, the actinides and the lanthanides. You'll see that because of the name of the element that is right before them. So the periodic table, actually, when you go from this element here, the next one would be here at the beginning, the first row of the F block. And then from this one, you go down here. So the periodic table is actually quite extended. It's wider than it actually is on what we would present as a normal periodic table. And that's just, it's presented the way it is here on the screen because it's a little more condensed. You pull the F block out and then condense it just for ease of reading and placing it on a piece of paper. But it actually is, in reality, that F block should be inserted right in here. Okay? But this F block, why is it called the F block? Because this is where the F orbitals are being filled. So here you're filling, this would be F1, be ending in F1, oops, sorry, F1, F1, okay? This would be F2, etc. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, because there are 7 F orbitals, each holding 2 electrons, a maximum of 14. Here you're going to be filling the D orbital. It's going to end in D1. So this would be D1, D2, D3, D4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why? Because there are 5 D orbitals, each having 2 electrons. That's why there are 10 rows for the D block. Okay? Now, I will say something as we look at the energy levels. There's going to be a little slight difference in the row number and the coefficient for D. So after 4s, we actually start to fill 3D. So this is 3D1, 3D2, 3D4. So here, this coefficient, the energy level that we're filling here in this D block area, this energy level is always going to be 1 less than the row number. And down here, when we start to fill this first F row, this actually, even though it is in the 6th row, you are actually filling the 4F. 4F gets filled after 6S. So here, the energy level, this coefficient is 2 less, sorry, than the row number, 2 less. You'll see this as we fill in these orbitals using the energy diagram in just a little bit. Okay. Moving on, let's read this part right here. Basically what this is saying is go now and share your information with other groups, but we kind of already did that. We already talked about it as if we had all of the information from the different groups. So it says count the number of columns in each of the 4 blocks and what is the relationship between the block size and the number of electrons that will fit in the corresponding atomic sublevel. So I just said that there are two columns for the S block, and that's because S holds 2 electrons. So you've got the S1 being filled, or S1, and then S2. S has 1 electron, one S orbital per energy level, maximum of 2 electrons in there. Then you've got the P block, you've got 3 P orbitals, each having 2 electrons maximum. That's why you've got 6 across there, 6 columns in your P block. And then as I mentioned, the D, there are 5 D orbitals times 2 electrons each. That's why you've got 10 rows for your D block. As I mentioned already, there's only 2 for the S. And then down here, the F, there are 7 F times 2 electrons in each. That's why you've got 14 columns for your F block. Where an element is located within a block in Model 1 and the superscripted, the raised like an exponent value appearing at the end of the electron configuration of that element. Okay, so here what they're saying is, let's go back up. Okay, so this is the group 1, group 2. So this superscript right here, if it ends in S1, that means it's in the first column in that block. If it ends in S2, it's the second column in that block. P1 tells me it's the first column in that P block. P2, second column, third column, fourth column, fifth column, sixth column in that block. Same thing with D and F. Okay? Obtain the electron energy level handout from your teacher. I've got that for you. It's in the assignment. It's in the course as well. And we're going to look at this electron energy level handout next to Model 1. Okay? We're going to start at the bottom, and then with the 1s energy level, and then locate the section of the periodic table corresponding to that sublevel. And then we're going to answer this question: why are there only 2 elements in the first row of the periodic table? Why are there only 2 elements in the first row of the periodic table? Well, let's look at our energy level diagram. Energy level diagram looks like this. All this is saying here is the electrons are going to fill the lowest energy orbitals full. Usually those first. Usually those orbitals are closest to the nucleus. The lowest energy ones are closest to the nucleus. So 1s gets filled first, then 2s, then the 2p orbitals, then 3s, then 3p, then 4s, and then it gets a little bit less logical, I guess, because we're going to start to fill the d orbital, and the d orbital, its energy position is in between the 4s and the 4p. Don't be so concerned about the numbering here. The number here is 3 just because we're going to go S, then P, then D, but the energy level tells us that the 4s comes before the 3d and then the 4p follows. So 3d, then 4p, 5s, 4d. This is how they get filled. This is the order in which they get filled, because we're going from low energy to high energy. Okay? So if I look at this, why is 1s the lowest? Because it's closest to the nucleus, and it only needs 2 electrons to fill that 1s orbital. That's it, 2 electrons. That's why in our periodic table there are only 2 elements in the first row, because 1s1, 1s2, now it's full. We've got to go to the next energy level now once we get a 3rd electron in an atom. And when we do that, we go up to the 2s. Then we start to fill the 2p. Once that's all full, then we go to the next energy level, which corresponds to the next row, and we fill the 3s. So that's why on the periodic table, we have s being filled with 2. The 3p orbital is being filled with 6. That's why we've got 8 electrons across the, or sorry, 8 elements across the second row and 8 elements across the third row. But then the fourth row, we have more space. We're further from the nucleus. We have more space. We can start to fill not just the S and the P, but also these D. And now you've got 2 columns here for the S. You've got 10 for the D, and you've got 6 for the P. More space as you move further away, higher energy, and more elements across that row. Now, let me just show you really quickly here a way that you can always figure out how the order in which these orbitals get filled. You don't have to memorize this energy level diagram. Let me show you just a quick way to do this. I'll find a little space here for you, and I'll show you kind of a neat way to remember this always. So you just list these different energy levels: 1s, 2s, then 2p, 3s, 3p, 3d. Every new energy level can accommodate another set of orbitals. We've got 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and there would be then a 5 something, maybe a G if we needed it, but we don't because we run out of elements, as you'll see. 6s, 6p, 6d, and again we're not going to need a 6f, 7s, 7p, and we're not going to need a 7d, but you'll see why. But I'll put it here, okay? Here's how you know what order they're going to get filled. You list them just like this. Again, I didn't put these here. All right, I didn't put those because we're not going to need them. We'll run out of elements before I need those orbitals. Now what I do is I'm going to draw diagonally across this diagram, and that is going to tell me the order in which these orbitals get filled. So 1s gets filled first, then the 2s, and I draw diagonally, and then I come back up to the upper right portion of my diagram and draw down again. So 1s first, then 2s gets filled, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, then 4d, 5p, 6s, then 4f, 5d, 6p, 7s, then 5f, 6d, 7p, and then the 7d if needed, okay? And we would keep going if we needed those, but we're not going to because we've run out of elements. But this will always give you the correct order, okay? Also, you can look at the periodic table. You always know the order in which they get filled because you just look at the periodic table. So 1s gets filled, then 2s, then 2p gets filled, then 3s, then 3p, then 4s, then 3d. Remember I told you the d, the energy level is always 1 less than the row number. 3d. The p block is always the same as the row number. 4p, 5s, 4d, 5p, 6s, 5. We're not going to go D here. We're actually going to jump down here to F. Remember, this would be inserted here. So it's actually 2 less than the row number. So it's not 5, it's going to be 4. 4F gets filled here. Back up here to 5D, 6P, 7S. Jumping down here, 2 less than the row number. 5F. Then back up here to 6D and 7P. Just look at the periodic table. You'll know exactly how they get filled, in what order, if you know that this is the S block, this is the D block, this is the P block, this is the F block. The S always has an energy level that is the same as the row, as does the P. The D is always 1 less. The energy level is always 1 less than the row number. The F is always 2 less than the row number. There you go. All right. We have here, work your way up the electron energy level diagram, locate as many sub-level sections as you can in Model 1. Why does the second row of the periodic table not have a D block? I already mentioned that. D blocks don't get filled until the the energy, the row where it has enough space, basically. So here you've got S, then 2S, 2P, 2S, 3P. You don't start to fill the D until after the 4S, just because that's where it's located in the energy position, and that's why it's found here in the fourth row. There's your D sublevel. Why then does the D block start in the fourth row? And that's simply because the 3D is higher energy level than the 4S. For the elements of the D block, how is the row number related to the principal energy level? So the row number is always going to be one more. So the fourth row is going to have the 3D being filled. So the row number is always one more, or I said that the coefficient here, the energy level for the D, is always going to be one less than the row number. Okay? We're not going to worry about this here. It's just talking about cutting out the sections as instructed and reassemble the periodic table sequentially by atomic number. If you did that, great, but we're not going to worry about that right now. Okay? All right, I mentioned to you that the periodic table actually is in this form, but you often see it in the condensed form because it's just a little more convenient to look at it that way. So this would be your S block here, this is your F block, this is your D block, and this is your P block over there. Remember, this is helium, which actually is filling or has full the S orbital. It behaves like the other noble gases, so it probably could easily be placed over here as well, because this would be your 1s2. Okay? So compare the periodic table model 1 with the periodic table model 2. What section of the table was removed? That would be your F block here, as I mentioned. That's pulled out and usually written below, and then the rest of the periodic table is pushed together. These symbols here are just telling you to go from that particular location and go down to the F block. That's where it continues, and then you come back and start at the transition elements again once you get to the end of a particular row in the F block. Okay? The form of the periodic table seen in Model 2 is called the long form. Makes sense? You do not often see this form in books or posters. The disadvantage is simply that it is too wide to put onto sometimes a piece of paper, or if it is put on a piece of paper, it is having to be written pretty small, and so it's just harder to read. That's one of the major disadvantages. The F block does not appear until the 6th row, and it fits in between the S and the D blocks. So explain this. We're just going to refer to the energy level diagram here. The F block, basically all you need to know is that when you look at the energy levels, the F block doesn't appear until way up here. It is a high energy orbital, and even though it's named 4F, just because you know, the 4D and then 4F, that just happens to be the numerical sequence that is used. It actually comes after the 6S and before the 5D and the 6P. So that's why it's located in the 6th row, and the 5F is located in the 7th row, just because of the energy position. So unfortunately, the numbering system throws us off a little bit. All right? For the elements in the F block, how is the row number related to principal energy level for the last orbital notation? So if you are in the 5F row, then that means the 5F block, okay, the 5F block, that means you are in the 7th row. So the row is always 2 more than the energy level for that F block row, and I mentioned that already. Okay? Write the last orbital notation in the electron configurations for the elements located at A, B, C, and D in the table below. You should not have to count electrons to do this if you understand the structure of the periodic table. So all it's asking us to do is write the last orbital notation, the last one. All we really need to know is where is it located in reference to the row, and where is it located in reference to the column. And we should be able to write the last portion of the electron configuration. I'm going to say this again, we're really concerned about that last portion of the electron configuration because those are the electrons, those valence electrons that are often involved in the bonding process of forming molecules and compounds. So right here, A, I know that A is going to end in 4 S block 1. First column of the S block, 4th row, 4s1. Okay? Let's come over here, C. C. I know that C, it's in the 5th row, and it is in the P block. P block, the row number is always going to be the same as the energy level. So I know this is going to be 5 P, and it is in the 1, 2, 3, 4th column across in the P block. So I know that 4 electrons have been used to fill the P orbitals. So 5p4. Let's look at B. B is in the D block. That D block, I know that the D block, the energy level is always 1 less than the row number. So if this is the 6th row, it's going to be 5D, and I have 1, 2, 3, 4, 5 rows across. And then finally here, D is in the F block, and I know that here this would be placed in the 6th row if it was the long form of the periodic table, and the F block is always going to be, its energy level is always 2 less than the row number. So here for D, this is going to be 4F, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4F11. Okay? Now there are exceptions to electron configurations, and we're not going to get into those. We might hear in the extension questions in a little bit, but I'm not going to emphasize them a great deal. But you might see some exceptions and some inconsistencies. You can look those up and discover why that is. Okay? Model 3. Let's wrap this up. Now that you understand how the structure of the periodic table relates to electron sublevels, you can use it as a cheat sheet, meaning you can look at just at the periodic table and you know exactly how those orbitals are going to get filled. The order of filling electrons in the sublevels of the atom. The following steps will help you write the ground state electron configuration for vanadium, V. So all we have to do is use your finger to trace a line across the top row of the periodic table. In Model 3, explain why the 2 boxes in that row represent 1s2. All we're saying here is, if you go from, where do you want to get down to here, V, okay? So if you just work your way across the periodic table, starting at the top and work your way down to V, you know you're going to start to create the electron configuration for vanadium as you work across the periodic table. So 1, 2, as I go across the first row, I know that the 1s orbital is full, so that's 1s2. If I work across the second row, I know I filled the 2s and I filled the 2p. That's why I now have added on 2s2, 2p6. If I work across the third row, I know I filled the 3s and the 3p, so that gives me 3s2, 3p6. And now I work across the fourth row, I will have filled the 4s, so I have the 4s2 filled, and then I go 3 deep into the D. Remember, D is 1 less than the row number, so this would be 3D, and I go 3 deep into that, so 3D3. All of these combined together will give me the electron configuration for vanadium. Not bad, huh? That's what all of this is telling you right here. Okay? All those steps are doing exactly what I just showed you. So using only a periodic table, we should be able to write the full ground state electron configuration for an atom, any atom. Let's look at tin, for example. Here's tin. I already have all of that written down. If I can just continue now, here if I go all the way across the D, this will become 3D10. And if I go all the way across this P block row here, that would be 4P6. And then if I go to the fifth row, that's 5S2. All the way across this D row, that's 4, one less than the row, 4D10. And then I come too deep into this P block on this fifth row, that would be 5P2. I combine all of this to get the electron configuration for tin. Okay? If you are given electron configuration but don't know what the element is, you can discover it. You should be able to figure out what it is. So all I have to do really is look at the ending of this here. I see what's been filled. Well, the highest energy level that is represented here is 7. I must be in the 7th row. I went through the S block in the 7th row. I went through the F row, the F block. That's the 5F, remember? That's still in the 7th row in the long version of the periodic table. And now I'm going to go 4 deep into the D block row on the 7th row. Remember, energy level is 1 less than the row number. This is our row, and I need to be 2, ignore the 14 because that F block is going to be pulled out, 2, and then 4 more. I need to be 6 across. 7th row. This is my S1, S2, and D1, D2, D3, D4. Whatever element that is right there, you have just discovered that element given that, that electron configuration. Okay? All right. Describe 2 different methods that could be used to identify the element. Well, I just gave you one. We use the ending portion of the electron configuration to discover what that element is. Okay? And by using the periodic table then, and knowing the order in which these orbitals get filled, we should be able to find any element on the periodic table. Okay? All right, we're wrapping this up. Here we go, extension questions. I mentioned that there are exceptions, and we're going to just mention some right now quickly. We're just going to kind of gloss over this. There's chromium, copper, and cesium. And these 3 here, there are exceptions. So chromium, we would expect it to have an electron configuration ending in 4s2 3d4. Okay? Because it is located right here. 3d4, 1, 2, 3, 4. Okay, so we would expect that chromium would have 1s2 3d4. But in actuality, in order for chromium to be at a lower energy position, it's easier for chromium to have actually the d orbitals, 1 electron in each of the 5 d orbitals. So it steals one from the s orbital and brings it over here to that 1. Remember, orbitals in the same sublevel, you put 1 electron in there first. So there's your d orbitals, but it's going to take one from this s and it's going to drop it in here into that 5th d orbital. That makes it a little more stable for whatever reason. Okay, so this, in actuality, this is what you would see for the electron configuration for chromium. All right. That is also true for copper, which is located right here. Copper, and we would expect the copper configuration to be ending in 3d9. But again, it steals one from the s orbital and fills those d orbitals, and it just is more stable that way as a result. Okay, and then you can look at this exception as well. This is what we would expect, but this is what we actually get. And the reason again is just it becomes a little more stable as a result of having this configuration versus the one that we would expect. Okay? All right, that is really all I'm going to say about that. Unless you've got maybe a question or two, you can bring that up in the class, and we can discuss that. Okay? So, periodic table, powerful tool. Now you realize the connection between the configuration of those electrons for a particular atom and the location of that on the periodic table. Why is it there on the periodic table? Because the electron configurations in a particular column are all ending in a similar manner, giving them all similar chemical and physical properties. And then you also see the periodicity, the repeating pattern on that periodic table as a result of how the orbitals are getting filled. All right, I hope this was helpful, and we will see you in the next video.